I'd like to introduce you to Peter Hanappe. Round of applause, please.
Hello, everyone. It's nice to be here. I'd like to thank Reshape for inviting me. So, my name is Peter Hanappe, and I work at the Sony Computer Science Laboratory. Now, first, just a quick word about what Sony CSL is. It's a research lab, a fundamental research lab. Quite small, we're just like less than 10 people. And we work on long-term projects. So we propose our own work. We don't work for, say, products. It's what we work on isn't requested like top-down. It's like from our own motivation. So we have a fair amount of freedom. But we also work with low budgets, so sometimes this is very explorative what we do. And a couple of years ago, I started working on sustainability and on sustainable food systems. And sort of the reference, the golden standard for sustainable food, I would say, is like Garden of Eden, right? Food just comes off the trees, a lot of biodiversity. I guess in those times, lions were also vegetarian. And I want to show like a farm in real life. This is a farm in Normandy, which has become a bit of a demonstrator in France about sustainable farming. It's called the farm of Becqueloin. And as you can see, they designed it also as a beautiful space, a little bit of paradise on Earth. Here you see some real pictures. It's not just a drawing. And there's a whole movement now in France, but I think elsewhere in Europe, US, about starting small farms that use, some people would say permaculture principles, other people would say agroecological principles. You pick your word. They go away from, say, principles from conventional agriculture. So they try to create a much more natural environment to grow food, see the farm as an ecosystem that you manage to make it productive, and use natural principles for pest control to maintain fertility. So I find this very interesting, these types of farms, for many reasons. I won't go into them now. Outside of, say, professional farmers, we also see a lot of citizens farming, using pretty much the same principles. Now, I only do a tiny bit of gardening in my spare time, and it's a physical activity, right? I don't know how many people here have their own vegetable garden, but you know, it's physical. And the people I know running these farms, they work very hard. So we started thinking, how can technology be useful for these small farms? Most of the major farming equipment producers are not really interesting in this audience. To be honest, they tend to use low-tech, and they do a lot of manual work, which has, of course, many advantages. So we wanted to look at what we can do, and we started working on robotics for these farms. And like I said, this fairly recent project, so we started about 1.5 years ago. It's very much bottom-up. And so we started designing a small robot. It has to be low cost. I mean, ideally, it's something that they can build themselves. So this is like an early prototype of what we were doing. I'd like to use wood for robots. I kind of like the contrast. And the main component is actually a component that you can find everywhere now. It's a CNC router. It's same technology as in 3D printers, same technology as in laser cutters. So fairly accessible and not too expensive. And with that, we can place tools very precisely in a crop, for example. So the idea is to make this robot go through the field quite slowly, accurately. Now it best works on flat fields. And then use numerical control to put tools in the field. And the first application that we're working on is weeding. It's not a very exotic application, but we wanted to do something that is very concrete for farmers. We wanted from the start to do something that is relevant to them. And from our interviews with them, we hear that up to 40% of their time they spend weeding, so it is relevant. And what we did is to take like a rotating weeding hoe, and we have like a top camera in the robot that detects the plants that are underneath it. We calculate like a path through the plants, and then twice a week we go with this rotating hoe through the cultures, to the crops, to stir the topsoil and prevent weeds from germinating. So it's actually fairly straightforward, and with our precise tool we can do just that. So we started testing it this summer, and it seems to be working quite well. Now, a next application, more long-term, that we're working on is to have some tools for farmers to follow up the growth of their crops. And we started using a 3D camera, an off-the-shelf 3D camera, a time-of-flight camera, the one by SoftConnected. I don't know if you know it. And again, the idea would be to use the robot to scan the plants in the field and to extract relevant biological parameters of the plant, for example, leaf size. And the data is useful in two ways. Try to pick up early signals for farmers about crop stress. But also what we think is interesting is to try to get this data back into agronomy labs. There's a field called phenotyping. It's mostly done inside labs where they try to find plants with specific features that are resistant, for example, in particular conditions. Like I said, most of it is done inside the labs. It's now starting to be done in the field, but we think it'd be interesting to really go out in farms and see whether we can find plants that have noteworthy characteristics, and then send this back to researchers. So it's just like the basis of our work, on top of which we can build like new applications for precise farming in these small farms. Okay. Another line of work that we're starting, we're happy we just got financing to continue work on this topic, and we start working with people at INRIA in France who work on virtual plant modeling, which opens a number of interesting perspectives. One of them is that if you want to use machine learning techniques, you need large data sets that have been annotated. For example, pictures of plants that you need to, a human operator has to annotate manually where the plants are, which is long and tedious work. And one of the ideas would be to generate synthetic images of plants and use this synthetic database, to train neural networks for extracting the information that we're looking for. And another topic is to, if you have the plant in the field, you grow a model of the plant on, say, on a server, to use this model to help you scan real-world data. This data helps you again to improve your models, so that you basically you grow the two in parallel, like your real field and your virtual field. Like I said, this is still we haven't started this work yet, but this is sort of line of work that will start next month. Now, there are a couple of things that working with this AI and in this field of agriculture, there are 3 points that I just like to close my presentation with. the first point is, what should we use AI for, right? Or rather, why shouldn't we use it for? I'm going to talk particularly in this field of, say, agriculture. Many people who start these farms that I just showed, they basically want, they're interested, they want a little taste of the mystery in life, in a sense, right? The natural environment is a very rich environment. It's beautiful. It's difficult to grasp. And in that context, trying to automate AI would not be like the good option, right? Because you don't want to put a barrier between the farmer and its natural environment. So we really should design the AI in terms of assisting the farmer, not trying to reduce the complexity of the farm, because this is, in a sense, what conventional agriculture has been doing, is trying to reduce the variability of your soil health, the variability in the seeds, the variability in weather conditions. And it's not to reduce this complexity, but instead to try to develop tools that help farmers manage the complexity, right? At least that's our position. We're not at the stage that we would be able to scan this and manage this, but it should be our goal in a sense. Another topic that I would like to raise. This is a picture of an association called Atelier Paysan in France. They develop open hardware tools for farmers, and farmer community is very much a DIY community, and they'd like to remain that way, or at least a significant part of them want to remain that way. So when we're going to put AI tools available to them, we have to make sure that they can keep their autonomy, that they can fix it, that they can understand how it works. I think is very important, and what we see in more conventional in the tools for more conventional agriculture, it doesn't go in that way. It goes more towards like closed solutions. You may have understood I'm very much like a defender of open source and open hardware. And this is also the type of spirit that we'd like to work in. And it's not just the open hardware and open software, but it's also about open data sets, because these will become more and more important to make sure these are accessible. So that's another point I would like to raise. And then the last point, it's not so much related with this work, but I'll bring it anyway. I'll maybe a bit moralizing, but it's the logo here, the slogan here is add volume and add value. But I'd like to add one point to that, is sort of add full life cycle analysis. I think this is also for the industry, technology industry, I think a major issue. I'm always a bit ashamed of using electronics while I'm working on sustainability, because I know that producing electronics is polluting, because I know we have a very hard time recycling electronics. Haven't got a solution for that, of course. But a couple of years ago, we tried to explore the question a little more, and together with a colleague, Mishka Melo, we tried to see whether we could produce temperature sensors using biosourced and biodegradable material as a sort of, very explorative project. And so we used bacteria to produce melanin, which is a pigment that you can also find in the skin. It's a semiconductor, and so its resistance changes in terms of, is a function of temperature. So we tried to produce melanin using bacteria, and then with a very much DIY setup, try to see whether we can make it work as a temperature sensor. Now, at the time, we didn't have funding to continue this, but what I learned from that is that this is a terrific challenge to try to go that way. And so I just wanted it to raise here today. Okay, that's all for me. Thank you very much for your attention.
Thank you very much, Peter.
Yeah.
I'll go ahead and take the Mando.
Thank you.